This is Lesson 30 of our Calculus 3 series. A series is the summation of terms in a sequence. So here we have the series a sub n going from 1 to infinity. This is a1 plus a2 plus a3, ... Now you might be wondering, is it possible to ever get a finite sum when you're adding up infinitely many numbers? And the answer to that is yes. Remember that we saw in Calc 2 with improper integrals, we saw this summation and found that it equals 1. Let's take another look at it. Here's the real number line from 0 to 1, and we have markers here at 1/2, 3/4, 7/8, 15/16, and so we're going to add together this distance of 1/2 plus this distance of 1/4 plus this distance of 1/8 plus 1/16, etc. And we know that if we keep adding in this way, we're going to get the entire distance from 0 to 1. So this summation is going to equal 1. Now notice the terms in our series here, 1/2 plus 1/4 plus 1/8 plus 1/16. This is a series where a sub n is 1 over 2 to the n. And this series is equal to 1. To examine whether or not a series has a finite sum, we consider the partial sums. So for the series a sub I here, I going from 1 to infinity, we consider the nth partial sum s sub n. So notice this is an infinite series, but we're going to take some finite partial sums here. Here, I is only going from 1 to n. This is just a1 plus a2, only up to an. So if the sequence of partial sums converges to a number s, and that's a real number, not positive or negative infinity, then we say that our series converges to s. And we write the summation of a sub I going from 1 to infinity, is equal to s. And s is called the sum of the series. If that sequence of partial sums does not converge, if it diverges, we say the series also diverges. So for the series we looked at above, k equals 1 to infinity, 1 over 2 to the k, we saw that this sum is equal to 1. Let's take a look at its partial sums. S sub 1 is k going from 1 to 1. This is just 1/2. S sub 2, k goes from 1 to 2. This is 1/2 plus 1/4. That's 3/4. S sub 3, k going from 1 to 3, 1/2 plus 1/4 plus 1/8, that's 7/8. And in general, we can see that the nth partial sum is going to be 1 minus 1 over 2 to the n. This is 1 minus 1/8. This is 1 minus 1/4. This is 1 minus 1/2. So in general, we have 1 minus 1 over 2 to the n. And we can see that as n goes to infinity, 1 over 2 to the n goes to 0, and so this limit is equal to 1. So our series converges to 1. Now let's take a look at this theorem. If the series a sub k, k going from 1 to infinity, is convergent, then the limit of the terms a sub k must equal 0. So what we're saying here is that if we're going to add up infinitely many numbers and get a finite sum, then those numbers have to be going to 0 in the limit. Let's take a look at the proof. Let's take a look at the nth partial sum and the n minus first partial sum. S sub n is a1 plus a2 all the way up to an, and Sn minus 1 is a1 plus a2 only up to an minus 1. And both of these partial sums have a limit s, because we're saying the series is convergent. Well, let's take a look at the difference of these two partial sums. Sn minus Sn minus 1 is just the term a sub n. So this difference is just a sub n, And let's take that limit as n goes to infinity. This is the limit as n goes to infinity of Sn minus Sn minus 1, which is the limit as n goes to infinity of Sn minus the limit as n goes to infinity of Sn minus 1. And we can separate and subtract like this because both sequences are convergent. These limits are both s, so this is 0. So this limit is equal to 0. So again, if a series converges, its terms must approach 0. That brings us to a test for divergence. If limit k goes to infinity a sub k does not exist or does not equal 0, then the series diverges. We just saw that if the series converges, the terms must go to 0. So if the terms are not going to 0, it can't converge. So this is a test for divergence. For example, if we have summation k goes from 1 to infinity of just k, that's 1 plus 2 plus 3 plus 4, etc. The limit of those terms is infinity, which is not 0, and certainly this does not sum to something finite. So that series diverges. But this is a really important example here. This series, k going from 1 to infinity, 1 over k, this is 1 plus a half plus a third plus a fourth, etc. These terms do go to 0, but this series does not converge. This is the harmonic series. We can see that the limit of the terms goes to 0, but we're going to prove that this series does not converge. And to do that, we're going to consider the partial sums S2, S4, S8. S2 here is 1 plus a half. S4 is 1 plus a half plus a third plus a quarter. But notice that this 1/3 is bigger than 1/4. And for convenience, we're going to make this inequality here. Put in the 1/4, and then this sums to 1 plus 2 halves. With partial sum S8, we have 1 plus a half plus a third plus a quarter plus a fifth, a sixth plus a seventh plus an eighth. And again, we're going to replace the 1/3 with a 1/4. We're saying this is bigger than 1/4. Also, the 1/5, 1/6, 1/7, they all get replaced by 1/8 because they're all bigger than 1/8. Again, for convenience, we're doing this so that we can regroup. This 1/4 plus a quarter is a half. These 4 1/8, that's a half. So we have 1 plus 1, 2, 3 halves. And if you follow the same pattern with the terms in the sum S16, you'll get that that summation is greater than 1 plus 4 halves. And in general, the partial sum S sub 2 to the n is going to be greater than 1 plus n over 2. So that says this sequence of partial sums goes to infinity as n goes to infinity. And therefore that sequence of partial sums diverges. And that says, of course, that the series diverges. So here we have a series where its terms go to 0, but it doesn't add up to something finite. And this is an important example to keep in mind. Now let's take a look at the geometric series. Geometric series are of the form a times r to the n minus 1, where n goes from 1 to infinity. So that's a plus ar plus ar squared plus ar to the third, etc. And of course here we're saying that a is not 0. So for example, we have 2 plus 2/3 plus 2/9 plus 2 over 27, and that is 2 times 1/3 to the n minus 1, where n goes from 1 to infinity. Here we have 1 minus 1/2 plus 1/4 minus 1/6 plus 1/8, etc. and that's negative 1/2 to the n minus 1, n going from 1 to infinity. I want to point out here that we could certainly write this as, say, k going from 0 to infinity, 2 times 1/3 to the k. Here, k is equal to n minus 1. Same thing here, we could write this one as k going from 0 to infinity, negative 1/2 to the k. In any case, let's continue. The geometric series is convergent when absolute value of r is less than 1, and in that case, the sum is equal to a over 1 minus r, and if the absolute value of r is greater than or equal to 1, the series is divergent. And this is what I just wrote above in purple. If we make the replacement k equals n minus 1, you could have your series written like this instead. So just be on the lookout. You can see geometric series that start at 1 with a power of n minus 1, or that start at 0 with a power of the index, power of k here. So for the examples we had above, we saw 2 times 1/3 to the n minus 1, and here we see r is equal to 1/3. And since absolute value of 1/3 is less than 1, we know this series converges to a over 1 minus r. So that's equal to 3 here. So here we have r is equal to negative 1/2, and again absolute r is less than 1, so we know this series converges to a over 1 minus r. In this case, a is 1, and we get 2/3. Here we have r equals 5, which is bigger than 1, and so we know that this series diverges. Now when we're finding sums of convergent series, it's helpful to make note of these properties. If we have a constant times a series term, we could pull that constant out of the entire series. And if we're adding or subtracting series and they're both convergent, we could add or subtract their sums. So let's take a look at these examples. We want to determine if the series converges or diverges, and if it converges, to find the sum. So the first one we have here is 1 over 2 to the k minus 1 over 3 to the k going from 0 to infinity. We notice that this is a subtraction of two geometric series. Right? This is 1/2 to the k, and this is 1/3 to the k. Since the r values for each of these are in absolute value less than 1, we know we can use our summation formulas for these two geometric series. And so this sum is 1/2, and we say this series converges to 1/2. Here we have summation k goes from 1 to infinity of 4k over k plus 2. And the first thing I notice here is that these terms are not going to 0 as k goes to infinity. Remember your limit rules. As k goes to infinity here, this is going to go to 4. Therefore, this series diverges. Here we have k goes from 0 to infinity, 2 over k plus 1. Now this looks similar to the harmonic series that we saw before, but the harmonic series we had 1 over k going from 1 to infinity. So if we just change the variable here, let n equal k plus 1, then this series can be written as the summation of 2 over n going from 1 to infinity. And this we know is 2 times the harmonic series. So that is going to diverge. Now let's take a look at the summation of 9 over k times k plus 3. And one of our tools from integration from Calc 2 is going to help us here. To integrate this, we would have used partial fractions. That's the same thing we're going to do here, so we could examine the partial sums. By using partial fractions, we find that we can write 9 over k times k plus 3 as 3 over k minus 3 over k plus 3. It's important to note here that we can't separate this into two series and subtract the results, because each of these series resembles a harmonic series and will diverge. And so that would give us something like infinity minus infinity, which we know is an indeterminate form. So we can only separate and subtract when we know that both of the series will converge. So here we need to use another method. And if we write it this way and start to look at the terms in the series, let's see what we get. When k is equal to 1, we get 3 minus 3/4. When k is equal to 2, we get 3/2 minus 3/5. When k is equal to 3, 3/3 minus 3/6. K is equal to 4, k is equal to 5, k is equal to 6. Let's take a look at what's going on here. When we get to k equals 4, we realize that we have a positive 3/4. Well, we had a negative 3/4 here. Those are going to cancel. When we get to k equals 5, we notice that we have a positive 3/5. And we had a negative 3/5 here. When we get to k equals 6, we see a positive 3/6. And we had a negative 3/6 here. So this term is going to cancel when k is equal to 7. This one will cancel with the term k equals 8. This one with k equals 9, etc. And so the only terms that are going to be left in this series are 3, 3/2, and 3/3. And so this is going to sum up to 11/2. More formally, we can look at the sequence of partial sums S sub n. When we take a look at S3, we have 3 minus 3/4 plus 3/2 minus 3/5 plus 3/3 minus 3/6. And then with S4, we've got all those terms plus 3/4 minus 3/7. And so the negative 3/4 cancels with the positive 3/4. And then in S5, we have an additional two terms, 3/5 minus 3/8. So again, we have our 3/4 that cancel. Now we have also the 3/5 that cancel. And so notice that the partial sums that we have here can be written in this form. 3 plus 3/2 plus 3/3. They all have the 3 plus 3/2 plus 3/3. And the remaining subtraction terms look like 3 over n plus 1, 3 over n plus 2, 3 over n plus 3. That's what we have here, 3 over n plus 1, 3 over n plus 2, 3 over n plus 3. Here, 3 over n plus 1, 3 over n plus 2, 3 over n plus 3. Same here. So for all n's greater than or equal to 3, our partial sum S sub n looks like this. And taking the limit as n goes to infinity, we can see that these three terms will go to 0. And so our sequence of partial sums converges to 11/2. And so our series converges to 11/2. Now let's take a look at another example. We have negative 1 to the k, 3 over 2 to the k. Well, when I see this 2 to the k and even the negative 1 to the k, I'm thinking geometric series. So I want to rewrite this by pulling out the 3 and combining these two. So I get 3 times negative 1/2 to the k power. And so now it's written as a geometric series. We can see that r is negative 1/2, so that this is convergent. But we have to be careful here. We know that when k starts at 0, this series converges to a over 1 minus r, which is equal to 2. But we're given the series starting at 3. So let's think about this a little bit. We want to know if this is convergent, and if so, to what? Well, we know that if it's convergent starting at 0, then certainly chopping off the first few terms will still give us a convergent series. But we do want to know the sum, so let's examine this a little bit more closely. This sum, starting at 0, gives us the terms 3 plus negative 3/2 plus 3/4 plus the series from 3 to infinity. And this entire sum is equal to 2. right? K going from 0 to infinity, this entire sum is equal to 2. So what's the summation here equal to? Well, just subtract off the terms. 2 minus a 3 plus 3/2 minus 3/4. And so this sum is -1/4. So we recognize that this one is geometric with absolute R less than 1, so we know that it converges, but we just had to subtract off the values of the first few terms so that we got the exact sum we were looking for. This will be the last example for this lesson, but let's take a look at the tools we have so far for convergence or divergence of the series. We know that our series will diverge if the terms don't approach 0. We know that a geometric series with absolute R less than 1 converges to A over 1 minus R, and with absolute R greater than or equal to 1, we know the series diverges. We could also examine the partial sums of the series to check its convergence or divergence. So far, these are the tools that we have for series. In the next lessons, we're going to see some more tools. And we'll conclude our lesson here on series.